Okay, so we've talked about one technique for solving transient problems analytically, separation of variables, and today we're going to start talking about sort of our second tool. There's other ones, but these are the two we're going to talk about in this class, and that's Laplace transforms. So Laplace transforms we can use for solving both lumped capacitance problems, and that's kind of where we'll start, but we can also use it for solving 1D or even 2D or 3D transient problems, right? And that's really where it becomes useful. You don't need this to solve lumped capacitance problems because we have other tools that work already, but you definitely do for some 1D problems. Here's the technique, sort of in a nutshell. You probably, or at least you might have encountered this in other domains like dynamics or controls. This isn't unique to heat transfer by any stretch of the imagination. It's a pretty generic technique. What you do is you transform the problem from the time domain into what we're going to call the S domain, and you do that with the Laplace transform, which we'll talk about here in a second. And the reason that you do this is because your derivatives with respect to time are removed by the Laplace transform. So what that means then practically is if you have an ordinary differential equation in the time domain, so maybe for example you have a lumped capacitance problem, when you transform it into the S domain, it becomes completely algebraic, right? And algebraic problems are easier to solve than ODEs. And in a similar way, if you have a PDE, so for example, our one-dimensional transient problems that were partial differential equations in both x and time. And when you transform that partial differential equation into the S domain, the derivative in time is going to go away. The derivative in x won't, but the derivative in time will go away, and so you're left with an ODE in x in the S domain, right? And that's really where this becomes useful and powerful. So the steps are laid out here. The first step is to Laplace transform your differential equation and maybe the boundary conditions, depending on your problem, into the S domain, where hopefully it becomes easier to solve, and then solve the problem in the S domain. And then finally you have to take that solution and bring it back to the time domain. So you have to use the inverse Laplace transform to get back to the time domain. And actually, typically these two parts of the problem are not that difficult. They're pretty, I'm going to say easy, but understandable, straightforward. This guy here can sometimes be a real pain in the butt to get it back to the time domain. So we'll talk about ways where you can sort of stop here and take your S domain solution and use it with numerical inverse Laplace transform tools to get back to the time domain. Okay. This is the Laplace transform. So just in terms of sort of our nomenclature, if I have some function in time, we'll call it f sub t. If I'm going to take the Laplace transform of that function in time, I'll indicate that with these, what are these, triangular brackets here, right? So this is the Laplace transform of f sub t. And then that Laplace transform is a function in S. Right, it's in the S domain, so it goes from being a function in time to a function in S, and we'll call that f hat sub S, right? So f hat sub S is the Laplace transform of f sub t, right? And the Laplace transform operation is just right here, right? You take your function in time, you multiply it by the exponential of minus st, and you integrate with respect to time from time equals 0 to time equals infinity. So if you look at this, we're integrating from time equals 0 to time equals infinity. So the result of this will not be a function of time. It will only be a function of s. Okay. That's what the Laplace transform is. We can just sort of demonstrate the Laplace transform using a very simple function. So the simplest function is one that's just a constant in time. So just some constant value regardless of time. If I want the Laplace transform of a constant, I would substitute this function of time in for this f sub t in my Laplace transform operation. So the Laplace transform of a constant is this integral right here, right? So this constant I can bring out. It's not a function of time, right? I can bring out of the integral. I'm then integrating an exponential with respect to time. So that would be minus 1 over s times the exponential of minus st. I have to evaluate these two limits. So I have the exponential of minus s times infinity and the exponential of minus s times, this should be 0, sorry, that should be 0. And the exponential of minus infinity is 0, the exponential of 0 is 1, so minus a minus is a plus. This is the Laplace transform of a constant. It's just that constant divided by s, right? So I can do this operation for any function. Typically, what you'll find is that this is used so often that tables and tables and tables of these Laplace transforms already exist. So you'll see tables like this one here, where you have a column containing functions in time, and then right next to it a column containing functions in s, right? And you'll see the very first one is the one we just did by ourselves, but these are all Laplace transforms of different functions. Okay, we can also use Maple to do Laplace transforms, so let's look at that for a little bit. Okay, the first thing you need to know in terms of using Maple for this is that the Laplace transform library is not automatically loaded when you open Maple. At least my version isn't. So in order to load the integral transform library, you have to type a command. And so at the top of your code, you would type with int trans. And what that's going to do then is load all these different functions. And the ones that we're specifically interested in are the Laplace function and the IMV Laplace function. And there's other ones here too that are pretty cool, but let's just focus on those. So Laplace, that function takes in 3 arguments, and it sort of makes sense. The first argument is the function you want to do the Laplace transform operation on. And then the second 2 are, what domain do you want to map from and what domain do you want to map to. So for us, we're going to be always mapping from time to s, right? So for example, if I wanted to know the Laplace transform of a constant, so let's look at this. I would do Laplace. The function is c, and I want to go from time to s. And what I should see is that that's c over s, right? If I want to know the Laplace transform of the sine of omega t, I would do Laplace sine omega t from t to s. And apparently that's the Laplace transform of a sine. So Maple's pretty good at this. You can see Maple's kind of good at inverse Laplace transforms as well, but actually not super good, as we'll see. So those are your options for doing Laplace transforms. And again, Laplace transforming from the time domain to the s domain typically isn't very difficult. And then solving in the s domain is also not that hard. So let's see if I can find my actual PowerPoint. Here we go. But then getting back from the s domain to the time domain is usually where you run into some hiccups. So the outcome of carrying out a solution in the s domain is very often, where's my cursor here? Very often this really complicated fraction filled with s's, right? And depending on the table you have, you're going to find that there is no entry for that kind of a fraction. So this is where you have to remember the method of partial fractions so that you can break a complicated fraction involving a whole bunch of terms down into more basic fractions or more basic terms that can be inverse Laplace transformed by inspection from the table. Right, so method of partial fractions is likely something you've seen before, but it's worth just sort of reviewing a little bit. So here's One of three different cases you might run into. This is sort of the most common case where I have this this fraction and it has distinct terms in the denominator, right? So I have s plus 1, s minus 1, and s plus 1. So in that particular instance, what I can do is break it into three fractions like this, one corresponding to each of those terms, right? And the idea being that I can't figure out the inverse Laplace transform of that big mess, but I can figure out the inverse Laplace transform of these three things pretty easily, right? I think they're just exponentials. So that's a pretty easy one. If I want to figure out C1, C2, and C3, what do? I clear the denominator basically, right? So I multiply this whole thing by s plus 1, s minus 1 times s plus 2. So that's what I did here. And then, of course, I only have the numerator on the left side. And then you can see the s plus 1 cancels with the s plus 1. So here I have s minus 1 times s plus 1. I'm sorry, s plus 2. Here I have s plus 1 times s plus 2. And here I have s plus 1 times s minus 1. So let's just go through and multiply these guys together. So this is, I guess, s squared plus s plus 2, right? Minus s plus 2s. So this is going to be s squared, and then I have a 1 and a 2 is 3s, and then 1 times 2 is 2, and this is s squared minus 1, right? So I pick C1, C2, and C3 so that this equation is satisfied no matter what value of s I have. So this is a lot like the method of undetermined coefficients. The only way that can be true is if all the s squared terms balance, all the s terms balance, and all the s to the 0th power or constant terms balance, right? So that's going to give me three equations in these three unknowns. And that's what I've done here. I have the s to the 0 power. So that's going to give me I screwed up, didn't I? I'm sorry. This should be the s to the squared power, and this guy is actually s to the 0 power. So the s squared terms are a 1, and then a c1, a c2, and a c3. That's this one. The s to the first power terms are a minus 3 here, and then you have a c1, a 3c2, and then there's nothing here, so that's this equation. And then the s to the 0th power are 4, a 2c2, a 2c1, a 2c2, and a minus c3. So that's this equation here. So you should always end up with three equations and three unknowns, and you can solve those, and that's how you get c1, c2, and c3. So that's pretty simple. You should know about two other possibilities that you might run into. So one being you have repeated factors in the denominator. So here, instead of having three distinct factors, I have two s plus 1s, so s plus 1 squared, and an s plus 2. If that's the case, then you have to include both powers of the repeated factor. So I'll have a c1 times s plus 1, but I also need a c2 times s plus 1 squared, right? And then you just do the rest of it exactly the same. Clear the denominator, equate like terms, and you'll get c1, c2, and c3. The other case is where you have a polynomial in the denominator that is greater than order 1, right? So all of these polynomials were just first order polynomials, s plus 1, s plus 2. I could have an s squared plus 2 term, right? So if that's the case, then I'll have the same term over here, but the difference is I need a polynomial that is one order lower in the numerator, right? So here I have a second order polynomial in the bottom. I need to have a first order polynomial on the top. Here I have a first order polynomial, so I just need a constant, right? And then you do the rest the same exact way. So that's that's how you do that. And then you can usually at that point invert Laplace transform almost by inspection. I did point out that there is an inverse Laplace transform function in Maple that works pretty good. It sort of works the same as this, except for with the IMV, so we're talking about this one right here. With the IMV Laplace function, the first argument is the function in the S domain, and then you want to map from the S domain to the time domain, right? So here, for example, maybe I want to do, let's make this a little bigger, IMV Laplace of C over S. That's my function in the S domain, and I want to go S to time. and what I should get back is the constant, right? If I put this guy in here, I should get back my sine omega t. So pretty handy. You're going to find that if you get too carried away with this function right here, Maple's not going to be able to do it. And so what you'll get back is just IMV Laplace. You'll basically get back exactly what you put in, which is Maple's very annoying way of saying, I can't do what you asked me to do. But that, that's a possibility. At that point, we'll resort to, like I said, numerical methods. We won't actually do the numerical methods, but some numerical methods to take care of that. Okay, here are some useful properties of the Laplace transform. We're not going to prove these. We'll just take these as fact. If you take 764, we'll actually prove some of these, the more important ones. The first one basically says that if you're taking the inverse Laplace transform of the sum of a whole bunch of terms, you can do it term by term, right? So I can take the inverse Laplace transform of the first term here and add it to the inverse Laplace transform of the second term, and so on. So we'll use this when we're actually taking our problem and doing the inverse Laplace transform. It basically means we can look at our problem, it may be a whole bunch of terms added together, and we can just tackle it term by term. This one says that if you take the inverse Laplace transform of a function times a constant, that's the same thing as a constant times the inverse Laplace transform of the function. So we'll use that a lot as well. This is the super useful property right here. This says if you take the inverse Laplace transform of a time derivative, so in this case I have an ordinary derivative of temperature with respect to time, I get in the S domain, S times T hat of S minus the temperature at time equals 0. Right? So this guy right here is really what makes the inverse Laplace transform so powerful. This is the same thing, but now written for a function that isn't only a function of time, but maybe also a function of x. And it says that if I have a partial derivative of some function of many variables, including time, with respect to time, that too becomes algebraic in the S domain, right? But now my t hat is a function still of x, but now of s instead of time, right? And then I have the temperature at time equals 0, which itself is going to be some function of x. All right, we'll use this when we start solving one-dimensional one-dimensional transient problems. And then this guy here basically says if you have a derivative in any variable other than time, it just goes to the S domain as it is, right? So if I have the second derivative of temperature with respect to x, which is what we'll get a lot in these problems, it becomes the second derivative of t hat with respect to x, right? So we're not making our problem any simpler in the x, in terms of x, only in terms of time. All right, so that's some really useful properties of the Laplace transform. And I think the best way to actually learn how to do this is with examples. So we'll do two examples. The first example is a lumped capacitance problem, just to sort of get our feet wet. It's one that we could have done without Laplace transforms. And then probably next time we'll do a second example, and that second example will be one that we couldn't do really any other way. That'll be a one-dimensional transient problem.